So my name's Owen. I'm a PM on the web platform team. I just wanted to get up quickly to point out that as most of us here are browser engineers, I think it's super exciting to have Ben from Facebook here today to bring the web developer's perspective. Over the past few months, we've been talking with web developers more and more, and I found that working with such an incredibly strong team as we have here from Facebook has been incredibly valuable. They bring a completely new perspective, and they know some issues really firsthand. And yeah, I'm excited to hear about what they do and how they think we can improve Chrome and the web browsers in the future. So, Ben.
Cool. Thank you, Owen. Sweet. So my name is Ben. I'm one of the tech leads on the WebSpeed team at Facebook. And I'm going to talk today about the infrastructure that we use to make the web go. What?
It's down.
Down. Oh, that makes sense. I'm going to talk today about a little bit about what the WebSpeed team does at Facebook. And basically, the first thing I want to do is I want to talk and tell you guys enough that if you go and view the source of the Facebook homepage, that you can figure out what we're doing. Because if you look at it, it's not HTML. It looks like a bunch of gobbledygook that we output. And so if nothing else, you will be able to debug what Facebook is doing if you're looking at it yourself. I'm going to talk a little bit about some of the things that we do to measure performance, and not just measure some number where, is it 1 second or 2 seconds, but how do we actually measure what is in that 1 to 2 seconds so that we can tell the engineers at Facebook what they need to do to make the site faster. Finally, I'm going to talk about one of our biggest challenges, which is that Facebook is a fairly complex app, and there's a lot of stuff going on the page. And what we found is that one of the biggest overheads is really the loading of a large amount of code into the page. And sort of talk about that as one of the big challenges that we see for browsers. So first of all, how do we build Facebook? What is on the homepage? And I think the first thing to think about, that to sort of put everything we're doing into context, is that if you design an application naively, and you just use the tools that are out in the open, what you tend to see is that you execute a bunch of stuff on your server, you send that stuff to the client downloads a bunch of JavaScript and CSS, and then it executes a bunch of stuff and it renders the page. And so all of this stuff happens in serial and there's no overlap. Now, for a site that's relatively cheap or relatively uncomplicated, only a few things going on, that's okay. But for Facebook, where we've got newsfeed, we've got chat, we've got all this stuff going on, that's a really big overhead because anything can just tank the performance of the site. And so what we do is we try to split up the work so that you're parallelizing everything, so that you do a little bit of server work, you flush it to the client. The client starts downloading some JavaScript and CSS. And starts executing that JavaScript and CSS. And that all of those things are happening in parallel, so you're taking full advantage of all the resources, the network, the CPU, our servers, and you're taking advantage of them all at the same time. And so the tool that we use to do this is called BigPipe. And the idea of BigPipe is you're incrementally rendering parts of the page called Pagelets. Pagelets are things like the composer, where you enter a status update, a newsfeed story, chat, the navigation. Each one of those things is an independent part of the page. We track the JavaScript and CSS that it needs independently, and we're able to render them as they come in on the client. So here's a snippet of something that kind of looks like what's in our PHP code base. We've got this awesome Pagelet, which is part of the page. It extends the Pagelet controller, and you've got this asynchronous function called genResponse, which calls another asynchronous function called genAwesomeMessage. So this could go to a database, Memcache, a thrift server, and it will execute in parallel with other things that are happening on the server. Once that asynchronous function is complete, we call this markup thing, which is sort of called XHP. It's a bunch of markup that we put into the code. And so in this case, we're returning a div that has the message, but it has this class where we've used this CX call. And CX is helping us package our CSS. It is saying that I've got this my style inside of the awesome CSS package. And it's doing two things. It's helping us translate that name where you can't use slashes in real CSS, and it's translating it into a minified name. And it's also hinting to BigPipe that before you render awesome Pagelet, you'd better download something that has the awesome package in it. So we have this class. What happens when you view the source of the Facebook homepage? You see this. So the first thing you'll notice here is there's this big HTML comment. And what we're doing is we're sending the markup that we generate from this Pagelet. And we realized that if we sent it as a JSON string, we'd have to escape a bunch of quotes and a bunch of other characters. And we measured that this actually, the process of escaping a string like this actually bloats the page by about like 2 to 3% after you gzip it. And so what we found was the most efficient transport for HTML is an HTML comment. So, so this HTML comment has got the div that we rendered, and you'll notice that the CSS class that we had before has been translated into a flattened name. Now, the next thing you'll see, sorry, overdid the clicking here. So the next thing you'll see is that there's this call to a script called BigPipe.onPageletArrive. And so what that is doing is that is saying, OK, BigPipe, I've got this Pagelet. Here's the markup for it. It's in the element P1. And I need this class called package.a.css. And so what BigPipe is going to do is it's going to say, OK, I've got this Pagelet. I need to download package.a.css, and once that's downloaded, I'm going to take that HTML out of the HTML comment and make it a real DOM node. And so what this does is this basically lets the developer say this very complex thing, which is I've got this portion of the page that requires this CSS. Make sure to download the CSS so you don't get unstyled content, and show it once it's ready, and expresses all of that without writing any real code to do it. So after this, you sort of do the before and after of the naively written page versus Pagelets. Pagelets have now taken all of this server CPU, and instead of having one chunk that you have to flush out, now you've got the red Pagelet, the yellow Pagelet, and the gray Pagelet. And when the red Pagelet is done, it can flush it out to the network. The client can start executing it. Now, I sort of skipped over something here, which was that I went from the awesome package to package.a.css, and I didn't tell you how I got from point A to point B. And what we've discovered is that even though you've got HTTP2, packaging is still really, really important. That there's so much overhead in going through all of the IPC within the browser that you're spending milliseconds of CPU every time you download something, even if it's in the cache. And it's also much more expensive to have lots of small packages because compression doesn't work as efficiently with lots of 1 kilobyte packages. The Facebook homepage has roughly 2,000 sort of modules in it, and having each one of those be a file would just be so much CPU, so much compression overhead, that packaging is still really important. And so this packager system, instead of packaging everything into one file, which would be really bloated, we take the resource utilization patterns that we see every day, and we automatically group resources. And so we are able to get something like 80 to 90% efficiency in terms of the number of packages we download versus the number of ones that we actually needed. And with that efficiency rate, if you take into account the increased compression that we get from having large packages, we're actually more efficient than if we didn't package at all. And so Packager is running, it's collecting data every day, changing packages all the time. Now, when we did this, we had a little insight, which was that the Facebook homepage, you go to the Facebook homepage, 99.9% of users are going to have feed stories there. And all of those feed stories require some of the same CSS. They require rounded corners on each one of the pages. They require JavaScript to render comments. And it'd be a shame if every time the user came to the Facebook homepage, we generated their news feed, and we were like, hey, we just figured out, we need those rounded corners, we need that JavaScript for the comments. And so the system called Early Flush analyzes the usage data from the page every day, and it says, you know, if the home page, if 99.9% of the time the rounded corners are required, then instead of waiting for newsfeed to generate and send out the package that I predicted, I'm actually going to say within milliseconds of the request coming to Facebook, I'm going to tell you, you need to download the rounded corners for newsfeed. And so visualizing this, what this does is this switches us from each pagelet requiring one round trip back to the CDN to download content. Now we predict all the resources early, which is in kind of blue in the after one here, and we are able to not spend a round trip time on any other pagelet because we're so good at predicting that it's only infrequently that a user has a resource that our predictor didn't say was going to be necessary. So I talked a little bit about how CSS uses CX call to sort of be a bridge between PHP and JavaScript. What do we do to talk between the server and the client for JavaScript calls? So we've got this API called JS call, where in my PHP code I'd say something like JS call foo, call the method bar, and pass the element my element. And what this is going to do is this is going to say, this is going to actually make a call to foo.bar, and it's going to pass in not the ID of my element, but it's actually going to pass in a real DOM node. And so I kind of want to talk about what does our JavaScript code base look like, and how do we translate that into actual JavaScript files that the user sees. So within Facebook, we use something that's very similar to the common JS system. We're writing code in ES6, so you would see something that looks like const helper equals require helper. You've got this foo module, and it's got a method bar in it, and all this is, again, ES6 syntax. And you say helper.do something with the element argument. And then you record that the foo module exports the object foo. Now, inside of what we do is our packager system figures out, foo and helper should probably be packaged together. And then it's going to transform foo into a module declaration that our JavaScript code base can read. So foo ends up looking something like this. So you call this function __d. You say, I'm loading module foo. It requires module helper. And there's this function, which we call a function a module factory. And the module factory is going to tell you how to construct the foo module. Now, the key thing we've done inside of here is you'll notice that the helper, instead of making a call to helper directly, we have now said require helper inside of the bar method. And the reason that we've done this is because one of the biggest overheads we see is in parsing JavaScript code. The Ignition guys came up here yesterday. They talked about how many sites have 20, 30% of their time spent in parsing JavaScript. And they also talked about lazy parsing. And the idea that the first time you run through a JavaScript file, you sort of figure out what the outline of that file is. And then once you call a function, you actually parse the inside of that function. Well, what happens when you load some of our modules is that the first time you load the helper module, you parse the outline of helper. And when you execute the helper module factory, then you actually have to parse the inside of helper. And so instead of requiring that the helper module is executed before you execute the foo module, what we say is that we just require that helper is downloaded. And when you call require, that will be the thing that actually calls the factory for helper. And so we're kind of going to great lengths here to take advantage of the way that lazy parsing works. And so this is pretty typical where this is something this optimization is new within the last 6 months. And it's an example of a time where we'll really go and talk with browser developers, view the source code of that browser to figure out how the browser works inside and what we can do to best make our code fit what the browser expects. So we've also got this abstraction called Bootloader. Bootloader is sort of based on this insight that if you write a bunch of client-side code, that you get these situations where one dialog opens another dialog, and all of a sudden your Facebook homepage has the JavaScript for creating an ad on it. And so Bootloader is a way that you can sort of sever these dependencies in a way that's asynchronous. And it comes with two APIs. It's got a declarative API and an imperative API. The declarative API is pretty simple. It says bootloader.load modules, the module name, and then a callback that takes that method, or that takes that module. We've got an even fancier system that uses React, where you have something called a bootloaded component that has a placeholder, which is a spinner in this case. It has a reference to the thing that would be bootloaded, and then it has a set of parameters that you pass to that module once it's completed loading. And so the combination of all this stuff, the bootloader system, the require optimization that we do, basically makes it so that we're deferring as much of the JavaScript parsing as we possibly can, and we're deferring as much of the code downloading as we possibly can. So given all this infrastructure and given all the context on how this stuff works, the next thing I want to talk about is how we measure things. So the browser exports all this really complex data called navigation timing and resource timing, which tells you a lot about how the internals of the browser works. But it doesn't tell you about what Facebook actually cares about, which is when does a site feel visually complete? So Facebook has two key measurement points that we use to define visually complete. The first one is time to interact. So what that means is from the time I go to facebook.com to the time that I see the minimum amount of content on the site. So that is a composer, first feed story, just the basic content of the site. The second one is display done, and that basically means that all the content on the site is still, that there's no layout moving around. It's, we've put all the content into the DOM that we intend to put in. So you got this tool called Artillery. Some of you guys that were in my session yesterday saw a real live demo of this tool. I don't have time to demo it here, but I'm happy to give anyone who wants a demo later in the day. But what it does is it pulls together all of the information that we can see from JavaScript. It pulls together the information from our server. It pulls together resource timing. And it puts together something that kind of looks like Chrome DevTools, but from a real user request. And we collect many, many, many samples like this every day. We aggregate them. We compute what was the critical path? What was the thing that could have been faster? And we use this to do analytics and do A/B tests to tell our product teams what can they do to make Facebook faster. So it might seem easy to measure stuff, but if you actually, I have like three little sort of trick questions here that kind of trick us up when we're looking at measuring things. So the first trick question here is you've got two pagelets, and these are flushed out by the server independently. The first one says, bigpipe.onPagelet arrive, it sends a pagelet, and then it marks pagelet 1 is done. The second script tag, which is generated later, says pagelet 2 is beginning, and then it says, bigpipe.onPagelet arrive. Now, you're looking at the statistics, and you see that pagelet 1 ended at 100 milliseconds, and pagelet 2 began at 700 milliseconds. So what could you infer from this? So the first obvious answer is probably that the server was slow at generating pagelet 2. That could be the case. The second thing you might be thinking is that there was trouble sending pagelet 2 to the client, that there's a TCP packet that got dropped, or that the user has a low bandwidth connection. That's also possible. But what you might not think is that pagelet 1 might have put some content into the DOM, and there might be a big style sheet recalculation and layout that happened. Or maybe an extension ran in between pagelet 1 and pagelet 2. Or maybe maybe there's another tab that's open that's in the same process, or an iframe that's consuming CPU. And so from our measurement tools, we can't tell the difference between any of these cases, because we only know when this second script tag got onto the main thread. We don't know when the browser actually receives it. So second trick question. You've got this very small beginning of the page where you have a script tag that says the environment, it's a production environment, and then you've got a script tag that says download myfile.js. And you see metrics that say the page started downloading at 300 milliseconds, and myfile.js began downloading at 700 milliseconds. So we experienced this. We came to the loading team, and we were like, guys, can you help us? And what we think is happening is that we think that extensions are able to run and are run as soon as the window is initialized. and that because preloads go through the main thread, that actually blocks the downloading of preloads. But from a developer perspective, we don't actually get enough data to definitively say that this is what is happening or to help debug it. And so a lot of times you see mysteries like this that you say, you're sort of like, hey, I need to go talk to my friendly browser vendor and figure out what's going on. So finally, Keynote screwed this one up. So imagine you've got this feed story that you render and you put into the DOM, and you've got another script tag that displays chat, and it says, OK, chat is done. Now, you go to your boss and you say, feed is displaying at 2 seconds. Are you correct? The answer is no, because feed isn't displayed, even though it's appended into the DOM at that performance mark. It's not yet visible to the user. It hasn't been laid out. And you actually can't guarantee that the display chat call is not run before feed is displayed. It might be that the browser says, hey, I've got time left in this frame. I'm going to execute another script tag. It runs display chat. Display chat takes 400 milliseconds, and it makes your feed story really slow. And so today, there's actually no way to measure when a piece of content actually shows up on the page, which means that all of our performance metrics.
Couldn't you mark it from a request animation frame?
You could. Someone earlier suggested the double request animation frame callback approach, because request animation frame comes before the layout happens, not after. So you've got to actually do the second request animation frame, which you could do, but that's overly conservative, right? That's telling you about sometime potentially after chat has displayed at that point. So it's a challenge, right? There's a lot of complexity to the way that the rendering stack works, and the point here isn't that that it's impossible to figure any of this out, but that often the performance metrics that are available answer some questions, but give you more questions to ask. And so there are many gaps that the current performance APIs, thankfully they actually tell you that these gaps exist. They tell you that the browser received something but hasn't started downloading your script. But they don't really tell you why. And it's very difficult, and the stuff that does actually tell you why, which is like the Chrome tracing API, is not usable outside of a lab environment. And the lab measurements, you don't get the right extensions, the right flavor of malware that creates the exact conditions that you need. It also triggers us doing a lot of workarounds. One workaround we've actually started doing, which is really terrible, is that we actually fire a timer every 10 to 30 milliseconds during the loading process. And if that timer hasn't fired, if at any given time that timer is fired, it hasn't fired for a while, we know the main thread has been busy. It hasn't been processing its queue of events. And we can infer that even if our JavaScript code isn't running, there's something else running on the main thread. It's not just idle and waiting for input from the network. We've also considered using request animation frame and triggering layout ourselves within request animation frame so that we can time how long the style sheet recalculation and layout takes, and we leave it so that we don't mutate the DOM after that, and that the browser is able to then not do any style sheet and recalculation of its own. And so sometimes there are workarounds that are available, but neither of these is particularly friendly to the user. And so we'd prefer to have better APIs to measure it. So the last thing I want to talk about is that Facebook is a really large application. And one of the challenges that we're seeing is that what we found is that the performance of Facebook is proportional to the code size. And that we're at a point where we actually have to tell developers, hey, don't add 5 kilobytes of JavaScript to the homepage. That's actually impactful. Now, it's probably been about 20 years before anyone else has been thinking about shaving 5 kilobytes from anything. Right? So the Facebook homepage is about 400 to 600 kilobytes of gzip JavaScript and CSS, which is a fraction of the size of a floppy disk. When I looked at my phone, the smallest mobile app I could find on my phone was a 6 megabyte app. That was the smallest app, and it was an application that was literally it was like an Uber for gas. You clicked it, and it delivered gasoline to you. That was 6 megabytes. Everything else was an order of magnitude larger. the 2048 game, everything else that I could find on my phone was an order of magnitude larger than even this simple mobile application. And on web, this 400 to 600 kilobytes is a performance bottleneck. And this 400 to 600 kilobytes comes after extensive pruning, after telling people, hey, like you really need to cut that 5 kilobytes, cut that 1 kilobyte of code. Now, if you look at about tracing at Facebook, what you'll find is that there's a significant amount of time that we spend in the parsing and compilation of code. Even the parsing of CSS is like 30 milliseconds on the page, which is a lot when you're talking about the context of trying to get the 1 second load in Rails. I kind of talked about how the module transformation that we do, in one way, it helps with the lazy parsing optimization. In another context, it doesn't. Because remember about how yesterday the Ignition folks said that sometimes you parse a function 2 to 3 times. In this function, you first do the pre-parsing of the entire function. Then you call the module factory. You have to parse everything inside of that. Then you call bar, and you have to parse everything inside of that. So by the time you've executed bar, you've actually parsed bar 3 times in today's JavaScript environment. One thing we did is we actually figured out, sort of by accident, that if you call the .length property on a function in JavaScript, that it forces the browser to do the parsing of that function. And this great new request idle callback spec came along, and we said, hey, maybe we could tell the browser, instead of lazily parsing, take the idle time, find all the functions, and parse them. And so, this actually made like a pretty big difference. And it's, I think that we do this kind of thing not because necessarily we think it's the best long-term practice for the web, but it's actually really useful to know that there is a bunch of idle time that happens while you're executing. That's why request idle callback is there, I think, because the idea is that sometimes there is computation that you can do while the user is idle, and that if you're idle for long enough, just doing garbage collection isn't going to help you after the 3rd time. But I think this is a lesson that, hey, maybe this is an area where we can work with browser vendors to say, we found that lazily parsing JavaScript in the background was helpful, and what can we do to take advantage of that idle time? So I think that the challenge of making large applications that are at Facebook size perform is a really big challenge, and something that both we, websites, and browser vendors have to think about over the next 1 to 2 years. There's a lot of challenges, in the background or in the network. Can we do background updates? Can we take advantage of the fact that on your phone, the App Store is automatically downloading the applications that you use and keeping them up to date? You never load an application and it never says, sorry, I'm downloading this from the Google Play Store, right? But on the web, if you go to Facebook, it says, hold on a second, I'm downloading the JavaScript code for this application. Can we do incremental updates to code? Facebook is moving to a model where we're going to be pushing the site a lot faster than we're pushing it today. And as much as we'd like to, we don't have the engineers to rewrite all of our front-end code every day. But we do change, maybe 1% of it, and that 1% causes us to invalidate all the packages that the user has cached. And if we can ship that 1% delta, we could be an order of magnitude faster in terms of the amount of code the user has to download. In terms of the CPU cost of extra code, we talked to the V8 team the other day. They suggested this idea of using eval to hide code from the JavaScript engine. So we tried it out. It's a crazy idea, but like Ojen said yesterday, all great ideas start from a really terrible idea. And we tried it out. The first version of it didn't give a performance improvement, but we're working with the team to figure out what will give a performance improvement. At some point, I wonder if it's a good idea for us to start shipping binary content, binary JavaScript, binary CSS to the client so that it at least doesn't have to do as much parsing. And there's no other language, no other client framework where parsing is a part of opening your application. And that's something that, as native apps have more and more code, that puts the web at a disadvantage, because for every byte of code I ship to the user has to parse that byte of code, or parse it 3 times, depending on how the lazy parsing optimization works. And finally, in any loading process, there's often idle time, and if we can figure out how to make use of that idle time, whether it's idle bandwidth, Facebook takes advantage of that by using early flush. If it's idle CPU, how can we fill those gaps with things that will help make the overall user experience faster? So just to kind of summarize, we've got a lot of infrastructure at Facebook that helps keep the site running fast. Everything from big pipes to Pagelets to Bootloader to Packager and early flush. We've got a really great tool called Artillery that helps us measure both the numeric speed of our site, as well as helps us debug what's going wrong. But oftentimes, the lack of APIs can make data ambiguous and hard to read. And that finally, the size of applications is actually a big bottleneck, and that a big challenge for the web going forward is figuring out how can we efficiently deal with an application like Facebook that's really big, it's updating maybe every hour, and the user wants to load it and wants it to feel instantaneous, similar to a native app. So thank you. Do you have time for questions? No?
We're technically on break now, so if people want to stick around and ask questions.
Yeah. All right, thank you.
Questions, just shout them out.
All right.
Is there something like a dark mode on the page where, like, when we're investigating something, we can see, like, the page that's arriving, slowing that down?
We have a little bit of stuff, so there's not a lot. There's probably a little bit that we could do. And if you come talk to your friendly Facebooker, we can help you debug what's going on a little bit. And I think over time, what I've found is even if I'm looking at the minified version of the code, I can actually figure out a little bit what's going on. But yeah, that's definitely a problem, and we've definitely had a lot of people ask that question. Yeah, so I think someone else mentioned that. I think we should probably take that into account, or figure out a spec so we don't have to do that.
Well, you can tell if you're in the background.
Right. Yeah. So sorry. The question here was there's a timer throttling on background tabs, and just sort of do we take that into account? And the answer is no. Right now we don't. But it's probably also worth us noting when we're measuring page load time. Does the page load time of a page the user doesn't see, is that important? Is that part of our goal? That's sort of a meta question. All right, cool. Well, I'll be around all day. We've got a bunch of other Facebook folks around, and so we're happy to answer any other questions you guys have. So thanks.